Hello, we're going to be looking at example 4 from your Pre-Calculus Part 2 textbook. This is found on page 793 of that particular textbook. It's example 4 under linear programming. Linear programming, folks, is a very complicated problem. It's not just a quick 2 or 3 step problem. Even though it is broken down into steps, these are complicated steps, as you know many things are in calculus. So to do linear programming, first of all, you've got to have an optimizing equation which has been given to you right here. This is the equation we're ultimately going to use to find the maximum or the minimum. And that's what solving a linear program problem is. It's using constraints, which are nothing more than these equations right here, to be able to find out what would be the maximum answer we could get and what would be the minimum answer we could get. And this is used in business quite often. So look at step 1. The first is we're going to graph these two inequalities here that are representing the constraints. X is going to represent the number of bottles of water, and Y represents the medical kits per plane. They can't be negative, and we need to graph the system of inequalities in quadrant 1 because we know that there cannot be negative 3 bottles of water, or there's no such thing as negative 5 medical kits. That's why it's bound to the first quadrant, because everything's got to be positive. Secondly, to be able to do these, we've got to graph these equations. And remember that you can graph by putting these into slope-intercept form. That's the easiest option. The other one I would guess would be to do the x and the y intercepts, which I think they've done actually here. So by setting y equals 0, you can find the x-intercept is 4,000. By setting the x value to 0, you can find that the y value is 8,000. And then they use the 0, 0 to determine whether you're going to shade above or below that. So the first equation is graphed over here in blue, and the second equation here is graphed in that purple color so that you can see the difference. So what they've done is they've gone through, put it in slope-intercept form, or again, you can find the intercepts for these to graph what's on the x-axis and what's on the y. That may even be easier for many of you. And they've graphed them. So the first one is graphed in blue here, and the second one, of course, is graphed in purple here. Now, both of them happen to be, as you'll notice here, happen to be less than. And so what happens is they're both shaded below. So if I shaded, remember x and y are boundaries here. So this is a boundary over here and this is a boundary right here. And then what overlaps, if both of them are below, then it ends up being below this line and it ends up being below this line. And the part that all of those tend to overlap in ends up being this section right here, okay? So all they did was they took this first picture up here at the top and just narrowed it down to it's this section right here that is your optimal space. Now, the thing about this is, as we begin to look into chapter 2, our maximum and or our minimum are going to come from one of these 4 vertices, whether that be 0, 0, whether that be 4,000, 0, whether that be 2,000, 4,000, or whether it be 0, 6,000. Your maximum and your minimums when you're doing linear programming always come at one of those vertices. Now, when we do that, what we're going to do is we're going to take those vertices and we're going to load them into that objective function or equation. Remember, they gave it to us at the very beginning, but here it is again. The objective function is 10x plus 6y. So let's start with the first one that I pointed out to you, which was 0, 0. If we plug in 0, 0 here for x and for y, our value ends up being a 0. Okay? Let's load in the second one, which happened to be this one right here. If I load in 4,000 for X but 0 for Y, then that's going to be 10 times 4,000 plus 6 times 0, or 40,000. So it ends up being that one right there. The next one is at 2,000, 4,000. So if I substitute in 2,000 for X and 4,000 for Y, that becomes 20,000 plus 24,000, which ends up being a total of 44,000. And then finally, the last one was if the vertices 0, 6,000 were put in, that would end up with a total of, and when I say put in, I'm saying put into the objective function or equation that was given to us at the beginning, we end up with 36,000. Okay? So I hope you can see that our maximum value, which they're calling Z, is 44,000. And now this occurs when X is 2,000 and Y is 4,000. That's when the maximum occurs. So in practical terms, this means that the maximum number of earthquake survivors who could be helped with each airplane shipment is 44,000. That's the number of people in general that could be helped. And this can be accomplished by sending 2,000 of the X, which was the water bottles, and 4,000 of the Y, which was the medical kits per plane. All right? So that's how this particular problem works. And again, it's very detailed. It takes a lot of time to be able to go through these steps. I know it's just listed as step 1 and step 2, but within these steps there's a lot of work to be done on that. So take your time, go through it methodically, just step 1, take a step at a time, and be able to do this. And when you're done, that is the process called linear programming. I hope this helps. Best of luck.